Hello everyone, can you hear me? I mean, I guess you were hearing my music, so I guess yes. Sorry, it's too loud. Okay, so someone is asking. Give me a second. Lecture 20 PDF. Okay, give me a second. So the PDF is already there. It should be here, right? Yeah, it's here. Shadows. Yeah. So we have the PDF already. Okay, good. So welcome everyone. We have 39 people. Oh, really? These are wrong? Okay, give me a second. Oh, it's true. Okay, give me a second and I can fix it. Okay, in the meantime, I have a couple of announcements. So the first is, I guess you're already working on your Theory 3 assignment. I guess that's important. Okay, if you said not yet, please, please start. Yeah, I don't want, we don't want to have problems for that, right? Okay, let's see. Yes, it's there. Okay, the PDF is already there, so please check it. It should be there. It's already fixed. Okay, good. So let's go back. Let's go back to the presentation. Okay, can you see the dragon? Yeah. Yeah, midterm grade. Again, so remember I finished the midterm grading a couple of days ago. So we were just doing the midterm extra. So yes, Jake is answering soon, very soon actually. Yeah. So we finished. We already finished, almost finished the extra. So Jake, I think we only need to combine them, right? I guess.
I guess I can speak about it. Yeah, it's almost done. I think after just a little bit more grading today, and then should be done. So like tonight or this weekend, it will be released.
Yes. Yeah, don't worry. And again, I mean the numbers are not as bad as maybe you were thinking. I'm not worried. Okay. So if the professor is not worried, you shouldn't be worried. Okay. Okay. Good. So let's talk about shadows. Today we will talk about shadows, and these are the announcements. By the way, give me a second. So first, you need to sign up for the face-to-face grading, right? Um, I think it's already posted on Piazza. I think it's recently posted. Remember, we have our transformation assignment, and it's super important for you to sign up on the face-to-face. So do that. Then, if you haven't started your Theory 3, please do that. Please start. If you haven't started, have you at least checked the PDF from the shader assignment? Say yes. Okay, a couple of people, yeah. The thing is, for the last assignment, we had a couple of people that they were literally beginning the assignment maybe 2 days before the deadline, right? I understand that you have other stuff to do, and yeah, that is, I understand, right? I also have a lot of things to do, but it's always better if you like at least start reading the PDF and things like that. At least your brain knows already like what is the problem, right? I understand sometimes we are, yeah, literally working very close to the deadline. It's not the ideal, right? But yeah, at least start. Okay, and also we will have a course survey because I've told you before on Piazza, it is very important for me to have your feedback, right? To know if everything is not, if something is not working on whatever, on lectures, on assignments, or anything. I really like your feedback. This is not my first time teaching, but it's my first time teaching this amount of people online, right? So, and yeah, I mean, we have a lot of technology issues, uh, right? Comparing with other lectures. So yeah, and also, I mean, also regarding the content, right? Also, I really appreciate your feedback. So No, I haven't uploaded, so I just wanted to tell you about it. The survey will be on Qualtrics. I don't know if you have heard about it. So I will post it on Piazza. Okay. I think I will probably post it maybe tomorrow, and maybe the deadline will be maybe on Monday or something like that. It is anonymous. You will have enough time to do it, right? But I need to tell you about it. Okay, good. So today you have a single learning goal, which is shadows. Okay, we will talk about shadows basically all the time. I was actually planning to maybe introduce geometry. That was actually my plan. I think the PDF it's called Shadows and Geometry, but yeah, I think there were we will have probably enough questions today, and yeah, I think we will probably not have time for geometry. Okay, so let's talk about shadow. Let's talk about the types of shadows depending on the type of light. Okay, so there are different types of shadows. Oh, sorry, give me a second. Okay, again, from now I will not read the chat because otherwise I just get incredibly distracted because I think that you are maybe asking questions and sometimes you're just talking each other. Okay, so types of shadows depending on the type of light. So we have basically three types. Sometimes we have subtypes, but yeah, this is basically what most people in computer graphics, either in technical area or artistic area, will agree. We have either directional lights or directional shadows, right, that come from directional lights, or the type of shadows that are produced from point lights and also from area lights. Okay, so let's discuss each in detail. So the first one is this one is probably the easiest. Directional light shadows. These are the lights that are basically the rays are parallel, and in that case the shadow doesn't grow depending on the distance to the light. I think we already discussed about this when I'm already talk about types of lights. This is basically what happens with the sun. Okay, so our sun is obviously a point of light, right? It's a single source of light, but it's huge and it's very far. Okay, that means that the rays of the sun are coming to us almost parallel. Okay, they're obviously not parallel, but they're almost parallel, right? So again, if you go out in a sunny day and you see, for example, I don't know, the shadow of a street light, right? You will see that the width of the shadow, right, is not changing as you are basically walking the shadow. Imagine that the shadow is very long, right? So basically the width of the shadow does not increase, right? And that is because the rays are parallel, right? In contrast, when the light source is a point, right, and is actually closer to the object, you have an effect. You have like a conic effect in which the shadow basically grows as it gets farther from the light. Okay, so in this case, the lights are coming all from the same origin, right? So they're not parallel, right? They're just coming from everywhere, and yeah, and you have this like conic effect, right? Okay, and someone is asking, but my shadow gets huge at sunset. Yes, that is true. But that is different. The thing is, imagine. Let me just change. It's a very good question. Yes. So if the sun is here, if the sun is, for example, it's like I don't know, if it's like 1 o'clock or something like that, the sun will be above the sky, right? It means that the shadow will be small, right? And yeah, you're totally right. Now, if it's the sunset, right now the source of light, the sun, will be kind of like here, right? And yes, the length of the shadow will increase. So imagine that I now take this source of light and I put it here, right? The rays are still parallel, right? So what will happen is that the shadow will increase its size, but it will increase in this direction, right? It will increase its size in the direction of the rays, but it will not increase the size on the orthogonal direction of the rays. Okay, so look at what happens when a light is a point light, right? Look at this growth, right? So it's not only growing in this direction, right? It's growing in this direction. You see? So this is basically happens because the direction of the rays. In terms of coding, I think I'm already told you about this. In terms of coding, when we are computing light and shadows from a point light, we need to get the position of the light usually as a uniform variable, right? And so we can calculate, for example, the light vector, right? Getting the position of the light and the position from basically the fragment that I'm computing the light. The same for the shadows, right? For the specific point from which I want to compute the shadow, right? I can compute the rays, right? Coming from this point. When we are talking about directional lights, when we are talking about sun, we don't even need to get the actual position of the light because only direction is enough, right? So in terms of coding, it's a little bit different. Just a couple of lines of code different, but it's a bit different. Okay, then we have another type of lights. They're called area shadows. Sorry, area light or area light shadows. So in this case, the shadow gets blurred depending on the distance from the light source. So quick survey. Which one do you think it looks more realistic? This one, or this one? Which one looks better? Yeah, area looks better, right? The thing is, in real life, right? Almost every light source that we have in real life is not a point of light. They're not single points of light, but actually areas of light, right? Because light is bouncing, right? Gloria is already telling correct. Area light because of bouncing light, of course. So for example, if you open your window, right, the light, even if it's from the sun, right, but the light it's coming from the entire window, right? So basically the shadows inside your room or the shadows when it's outside, right? Yeah, they're basically have this effect. So yeah, unless you're like in the desert, maybe at 1 p.m. at the desert, right? You will have usually area lights and you obviously area shadows. The thing is, okay, how can we get this type of lights? So let's talk about area light shadows. How this works, how we can actually implement this. So let's assume for a moment that instead of having a single light and single light source, you have a second light source, right? So look at the difference here. Can you see my mouse? Yeah, right, I guess. Okay, so look at the difference here, right? So this is having one light, this is having a second light. What is happening is this small portion right here, right? It is lit by one of the lights, but not basically gets light from maybe the first light, but not from the second one, right? So basically, each light is creating a different shadow, right? And is illuminating areas that the other light is not illuminating, right? So instead of having maybe two lights, now imagine that we have four lights. So you start to see this effect, right? That the inner part of the shadow, right, gets darker, and the outside of the shadow, right, it starts to get this like spreading effect, right? And it is probably intuitive to understand that this spreading effect happens in or is distributed or it's scattered in a larger area when the point you are computing is farther from the origin of the object, right? So as you are closer to the object here, we cannot see we are almost not seeing this effect, right? Because the difference in angle at this point, the difference in angle from the lights here is almost unnoticeable, right? However, as you're like walking in this direction, it gets way more spreaded, right? You can see this. So now let's assume these are basically four lights. Now let's assume that you have 21 lights and they're basically forming like an area, right? So this will be the effect, right? You have 21 shadows and each of those shadows are basically either occluding or not occluding different areas from the floor, and you get this this effect, right? I mean, this doesn't look very realistic, but this is basically what happens if you have multiple light sources from a specific space, right, with different positions in space. So if you just think about it and say, okay, let's imagine that there's not 21 or 50 or whatever amount of lights. We have just a infinite number of lights, right? Creating this like area panel or area light. Well, this is what you get, right? This is what you get when you have like a theoretical infinite number of light sources coming from a single area. The thing is, in terms of implementing this stuff, we obviously don't compute an infinite number of lights. That will be incredibly expensive, right? So area lights are usually computed with something called sampling. Whenever we are computing the shadow for a specific point on the floor, right? And we are and you will see how we do that, right? But it doesn't matter the algorithm you are using. When you are computing the shadow, right, for this point, for example, here, what you do to achieve this thing of area is you basically compute, for example, the angle to the vector to the light. Instead of computing the exact vector to the light, you basically take that vector and you randomize a little bit the position of that vector, right? And you basically compute that several times. So you do many samples for each pixel, right? You say, okay, I will pretend that there are several lights, right? So I will get different samples, right, from this specific pixel, right? So the thing is, it gets very expensive, right? Depending on how are you computing the shadow, the algorithm that you are using, if you're using ray tracing or not, or whatever. If you're computing, if you're, for example, using ray tracing and you're computing your shadows without any area light effect, maybe your rendering is taking, I don't know, 2 seconds. If you increase maybe 10 samples, right, and you randomize those things, well, it's almost like having to render 10 images instead of 1, right? So your rendering time will increase by 10, right? So these effects are very realistic, but in general very expensive. And again, we will keep talking about this. We will have several lectures on ray tracing, and we will actually code and implement the ray tracing, and you will code area lights for your ray tracing. So you will see that it is very fun. It is challenging, but it will be nice. Okay, good. So obviously, depending on the size of that area, right, is basically the effect you get, right? So if the area is smaller, you will get a different effect. And I have a question for you here, and this can actually be a question for the quiz today. There are two areas in a shadow, and I mean you can Google this obviously, but there are basically 2 areas in a shadow called umbra and penumbra, right? So those areas are basically the darker area and the area that is like not totally blocked by the shadow, but also is not completely lit by the light, right? So a possible question for our quiz today is which one of those is the umbra and which one is the penumbra, okay? Yeah, so we can, so probably saying the darker is what? The umbra? Okay, so probably saying the darker is umbra. So you're saying that the penumbra is the outer side? Guessing? Okay, good. Okay, you can Google it. But yeah, you can Google it. It will be on the quiz. Okay. So, in terms of quality, area lights and area shadows in general are basically standard for realistic rendering. So, it doesn't matter if it's if we are talking about real-time rendering or online rendering, or we are talking about ray tracing rendering, right? Yeah, basically, if you need to create something like very realistic, you definitely need to compute area lights and obviously area shadows. Yeah, it's an heirloom food, of course. Yeah, I made this. I have a friend, a very good friend of mine. She is a designer for. She basically is her work is to design this type of objects for airlines. So I made this render for her. It actually is not the final render because as you can see it has like noise here. I don't know if you can notice. There's a bit of noise. So these are not the final renders. But I wanted to for you to see this because the shape of this these shapes here this area shadow is very obvious, right? I mean, you can see that the shadow here is it's way more defined, right? And it's basically is like spreading out, right? Or getting diffused in these sections, right? So yeah, realistic rendering will be always area lights. I think these designs are for a Saudi Arabian airline. I don't remember exactly. Okay, so break questions. Okay, Nam has a question. Yeah. Yes, Nam.
Hey, so when you compute the area light, I'm imagining each virtual point light has to have very small intensity. Is that the case? Because I imagine the darkness of the shadow would be proportional to the brightness of the point light.
Okay, so the way you compute the color for your fragments is, let's assume that is using a Bling, right?
Right.
So you're computing the color. The thing is, you can use, for example, the shadow information. You can use it as a multiplier for your diffuse and specular components, right? So to literally just make your colors darker, right? So when you're computing the shadow, what I mean, let's imagine that is let's assume that is not area shadow. Let's assume that is just like plain shadow, right? With a very hard edge, right? Basically,
Yeah.
the shadow will be like a boolean, right? Either 1 or 0. So you can define it. Okay, if it's 0, I will decrease, right? I will decrease the color of my objects in this amount, right? So for example, here, I could you could also decide. Give me a second. You could also decide, for example, to assign to all these objects to assign like totally black color, right? But that will be basically also decrease your ambient component, right? So for example, here I'm not decreasing the ambient component. I was only decreasing the diffuse and specular components. So the question is, when it's an area light, instead of being Boolean, right? Now you will have, right, a range of values. Those values could be basically from 0 to 1. So depending on how is this pixel affected or not by which area or which, right, which portion of the area light, you will get a value from 0 to 1, and depending on that value, those will be your weights that you take to either like obscure or not your colors, right? Is that what you were asking, or?
Sort of. So I was imagining, basically you want the intersection of all shadows to be darker. So it's similar to setting an alpha value, small alpha value where the shadow is supposed to be very dark, and then
Yeah,
the intersection would be the darkest.
yeah, it's very similar. Yeah, yeah, sure. Okay. Can is asking, can we determine how many lights are there according to the shadow? Very good question. I don't. I mean, if it's I mean, if it's this case, maybe you could. But if the area shadow has like a very good quality, maybe not. I mean, this question is impressively interesting, Can, by the way. Because what I'm thinking right now that maybe what you could do, for example, is maybe not maybe not determine how many lights you have, what you could do is determine the size of the area the size of the area light. So sorry, I'm thinking a lot right now because Can just made a amazing, beautiful question that is incredibly interesting. And let me tell you why. What Ken is asking is basically, okay, if we are seeing a shadow, what information could we infer just by seeing the shadow, right? Okay. The thing is, if we are talking about either real-time rendering or ray tracing rendering, it sounds like we don't need to do it, right? Because I mean, whatever, it's a it's ray tracing and that's it. The thing is, and why this question is so relevant, and thank you for asking this question, is it's very common for us in computer graphics to we need to sometimes um, to render objects and to basically put objects on a real scene, right? That happens in movies. So for example, if you are seeing a movie in which they have a monster that is basically destroying the city, whatever, they could have a plate or a shoot, right, from Vancouver, right? I mean, a real filming thing from Vancouver, right? And basically what you need is you need to create a 3D Tyrannosaurus, right? And you need to put that Tyrannosaurus on top of those real images, right? So that is incredibly complicated. Matching the light from a 3D object with the real light, right? You basically took like either from a photograph or from a filming situation. It's incredibly hard. That is one of the most complicated things that happen in a shooting in a movies thing. So for example, I have a couple of friends that I have one friend in particular that he's basically in charge of the lighting at ILM, Industrial Light and Magic. This is the company that basically does all the Star Wars movies and Avengers and all those movies from Disney, right? So one of the goals from his department, because he's like the supervisor of the lighting department, is that whenever the crew is basically filming a plate, right, like a real plate. Imagine again that you will film, I don't know, a battle scene, right, and you are filming a real street, and you will put, right, like not real things in 3D on top of that scene. People from his department need to go there, right? They need to go to the shooting location, and they need to take a lot of information and photos and metrics and a lot of information about the lighting at that moment, because basically they need to mimic exactly the same lighting digitally to, right? Otherwise, basically the objects will look fake, right? So this question is incredibly interesting because what if this could be possible, for example, imagine that you go to the shooting and you take these pictures, right, or you have like the original picture that they took on location, and you could have like an algorithm that can just by seeing the real shadows, like deduce or compute where was the actual position and size of the real source lighting sources, so you can just grab that information to like mimic that in your 3D scene. That will be incredibly amazing. I think, yeah, sounds incredibly complex. It is. I think maybe that is probably a problem solvable in deep learning. There are a couple of papers from SIGGRAPH that I've seen. They are basically matching lighting that already exists. So I haven't seen like a specific work on deep learning that is literally matching exclusively shadows, but there are some SIGGRAPH papers already from which you can take again like photographs from a scene, and you have a 3D model with a certain lighting, and you can modify the colors of your 3D object to basically automatically match the lighting and the color grading from your real scene. But yeah, those basically, yeah, those questions that maybe happen like in a lecture like this, those questions can become the the PhD research from someone, and they can become a silver paper, and then they can become a Oscar technical achievement award, right? Yeah, very nice question. Okay, so let's continue because we have a lot of things to talk today. Okay, so we have other types of shadows depending on the algorithm we use. Okay, so for now let's assume that for all my following slides I will use the point light paradigm, right? So using point light paradigms, I is okay. How can we compute the light, right? We either use a ray traced approach, or we use a shadow map approach. So the ray trace approach, it is usually on ray tracing rendering, of course, and shadow map is what we usually do in real time rendering. So, for example, in WebGL or 3.js, this is what we usually use, shadow map, and it's so basically this is like a very realistic, geometrically precise way to compute shadows, and this is the fake one. Okay, remember, computer graphics, real time rendering, we always go for the fake effects, right? The fastest. Okay, so ray trace shadows. What is the algorithm actually doing? So basically, for each pixel in the image, so obviously this is our camera, right? This is the image, and we are the camera here. So imagine that you shoot a ray from the camera to each portion of your scene, right? For every pixel, you basically shoot a ray. So let's imagine for a moment that I'm shooting a ray and it's hitting in this position right here. I created like a small red sphere, okay? So once you're there, what you do is now you shoot a secondary ray from that point in particular. You throw a secondary ray to your light source, okay? So if that ray is blocked, right? So basically when we use ray tracing technology, right? A ray is like a laser beam, right? That is basically traveling, and whenever you hit a surface, you know that you hit a surface. So if it's blocked, it means that that portion of this that surface is just shadow, right? So it's very easy. It's incredibly easy to implement, and well, this is an example in which the secondary ray is obviously not blocked. It means that this surface right here, or this pixel right here, is not blocked, so it's not under the shadow, right? So ray trace shadows are super easy to implement. Geometrically speaking, it's very simple, okay? The thing is, they're expensive because you need to shoot rays, at least two rays, right? You need to shoot one ray to get to the surface, and then another ray to get to the light. And if you don't have a single light, you need to shoot a lot of secondary lights. And if those lights are not point lights, but they're actually area lights, the number of secondary lights that you need to shoot there, it's impressively huge, right? So imagine if it's an area light, I don't need to send a single ray, right? But multiple rays, basically sampling the entire area, okay? So we are talking about like impressively complicated scenes. And just for you to imagine, again, I was telling you about this friend of mine. His name is Daniel Smith. So he was, for example, in charge of the lighting from I think on the first Avengers movie, there is a scene in which you can see like the hangar from the helicarriers. I don't know if you remember the scene, right? So like people is talking, and you can see like a huge hangar with a lot of helicarriers. That scene at that time, when they were basically doing that movie, that scene broke the record of having the most amount of lights in a single scene, right? In a single 3ds Max scene, because they're using 3D Studio Max to create these environments for those movies. So in 3D Studio Max, they basically broke the record. That he created that scene. He created the lighting for that scene. So he had, if I remember correctly, he had more than 10,000 lights. So the scene of the helicarriers had 10,000 lights. Yeah, and at that time was like a huge technological achievement to create that scene in particular. So it is very expensive. Okay, questions about ray tracing shadows? Which scene is this? I think it's on the. I think it was on the first Avengers movie. Maybe I'm wrong, but there's a scene in which you can see the hangar, right? When they have like all the helicarriers, these like huge flying ships, and yeah, that's the lighting of that scene was like impressive. Right? I mean, this happened a long time ago. That is 10,000 lights right now is almost nonsense. Yeah, you have obviously more. Yes, Yushin, you have a question.
Yeah, I'm kind of confused about the difference between the first ray and the second ray.
Oh,
So you're saying like the first ray is from the light to the object?
no. The first ray is from the camera. So basically, we are the camera, right?
Yeah.
So it's from the camera to this object. So basically, you cannot see the ray. That's why I didn't draw the ray, because we cannot see the ray, because the ray is basically beginning here on the camera plane and is hitting here on this surface, right? Because it's literally coming from the camera. It's like your eyes are. Imagine that your eyes are is that ray is basically your eyes, right? Your eyes are shooting that ray. So that ray is just to get to this surface in particular. Then, already on this 3D scene, you shoot another ray, the secondary ray, on the direction of the light, right? And if it's blocked, it means that you are on the shadow, right?
Oh,
This
yeah.
in this case is very similar. We first shoot an array to create basically, or to get into this like red sphere, right?
Mhm.
And then from here we shoot another array. So this is the secondary to get to the light source, and in this case it's not blocked, right? So it means that it's not a shadow, right?
Okay, I got it. So the first ray is just to like pivot a point or some point on the surface, right?
Yes, and it's coming from the camera, which in this case is like coming from us, right? Because we are the camera right now, right? That's why I cannot express visually that ray in this image, because it literally comes from us, right? It is there on my mouse, and this is the secondary one.
Okay.
I will probably what I can do is I will create a different render. Maybe I will modify the PDF. So I will create another render in which we can see maybe the same scene, but we can see the camera. So I can maybe show like the two rays, the one that is coming from the camera and the one that is going to the light. So yeah, I will modify the PDF thanks to you, and I will maybe that will be clearer. Yeah.
Yeah, thank you.
You're welcome. Okay. Nami's asking, why bother computing the first collision point? We could just discretize the entire scene and compute rays from each fragment to the light source. The point line is going to hit them anyways. Yes and no. I mean, I don't know what you mean to discretize the entire scene. The thing is, the plane that is representing the floor in this case, right? It has fragments that are basically on the other side of this column, right? Those fragments are already occluded by this column. So why do I need to compute if there are shadows on those fragments if they are not visible, right? So I compute the rate because, right, I only need the parts that are visible.
Well, I guess I'm thinking of just sampling from the entire floor and shooting the rays from each sample point.
Which I agree. The thing is, not all the fragments from the floor are visible to the camera, right?
I see.
Yeah. So if yeah, you're basically wasting a lot of information. Yeah. Okay. So let's continue. Now let's talk about shadow maps. shadow maps are basically, this is the technology that we usually use for video games in real-time rendering. So this type of shadow maps, they basically, we need to at least compute 2 shader passes. So the first concept that we need to understand is we need first get to get a render from the point of view from the light source. Okay, so imagine that I put a camera here and it's looking to this object right here. This will be the render, right? So we cannot see the shadow here, right? And it makes sense. If I am rendering the scene from the point of view from the light, and the light is the one that is causing the shadow, right? Basically what it means is that the shadow is basically behind the object, right? So I cannot see the shadow. Right? You agree, I guess. The thing is, this render that we need to take from the point of view from the camera, sorry, from the point of view from the light, we don't need to compute colors. We need to compute a depth map. Okay, so for each pixel, we only need to compute the actual position, right, from those fragments, but also its distance to its distance to the light source. Okay, so for example, in this case, this area is wider, right, because these parts are basically closer to the light source, and these are farther from the light source, or they are like becoming gray. Okay, and we do this, we get a shadow depth map for every object on the scene. So for example, in this case, this is only the depth map from the column, but you also need to get exactly the same. You also need to get the same depth map also from the floor. And if you had 25 objects on the scene and you had, like, I don't know, the pumpkin and the whatever, right, a teapot and the Stanford Bunny, whatever. If you have 20 objects, you need to compute 20 depth maps from each object, not from each object, sorry. One depth map from each object, so of course 20 or 25 or whatever amount of objects you have, for each light also, right? So you need to compute a lot of depth maps. For each object in the scene, you need to compute a depth map for each light. Okay. Then what do we do with that information? So basically, again, as I said, we first get the render, but we need to render the depth map instead of color, right? So this is the depth map. So then we compute the camera view, right? So we compute the actual view with the camera transformation and everything. And for each point in the surface that we are basically computing the color, remember this happens in the fragment shader, right? So in the fragment shader, I get into this fragment in particular. And for this fragment in particular, I need to find the corresponding depth map pixel. So basically, because I have this information, right? I have this map, and this map I need to have the depth information, but also the coordinates of those fragments in 3D, right? So basically what I do is I get into this fragment here, I get the coordinates in 3D of that fragment, right? Basically the portion on the floor of that fragment in particular, and I search for the closest point, right, from this image, right? And let's say that I get into this color right here. So this pixel right here, if it's basically the same position, it has the same position of this guy, right? Now I have two depth values, right? I have this value, which is basically the distance from the column surface to the light, and I have now this fragment here, from which I can compute the distance from this point here, where my mouse is, to the actual light, right? So which point is closer to the light? The one that is stored in the depth map, or the one that is touching my mouse? Which one is closer? What do you think? In this case, and nobody's answering. Don't worry. So the one on the surface is closer, right? You agree? So basically, if the distance from the fragment that I'm computing at that point, its distance to the light is larger than the corresponding distance that I have on the depth map, it means that that fragment is basically behind something that is visible from the light source. You understand? So if you're behind of something that is visible from the light source, it means that that something is basically covering, is occluding the light source from you, which means that you are under shadow, right? And that is how shadow maps work. So shadow maps are way faster than Raytrace Shadows, and they're they're very convenient. They also have some drawbacks. So for example, and this is just another example, right? In this case, I have the Stanford Bunny, and it's the same. I basically take a depth map from the Stanford Bunny. As you can see, these gray areas are basically telling me how far this surface is from the light source, right? And again, if I get into this fragment in particular, let's assume that maybe this fragment corresponds, right, to maybe the fragment on the eye. If I compute the distance from this fragment in 3D, right, the distance from this fragment to the light source, its distance is obviously larger than this distance right here, that is the distance from the eye to the light. It means that there's something that is blocking me from the light, means I am in the shadow. Yeah. And Garlic is saying, can you repeat that again? Yes, I can repeat. Okay, again, the way shadow maps works is I have a depth map which has from the point of view from the light, you have information from the surface of that object in particular on how far or close is the surface of that object with respect to the light, right? So basically, imagine that we are talking about the eye from the bunny. Let's assume that the eye from the bunny is kind of here where my mouse is. It means that it could be maybe here, right? So this color right here from the depth map is basically, or is telling you the distance from this portion of the surface to the light. Okay, so this distance basically is encoded on this color right here. When you're computing the light for every object, and you're computing the lighting for the color, for your floor, right? And you get into maybe this point here, right? You need to find which is the corresponding pixel, right? Let's assume that is this pixel, which represents this guy here. And then you compute the distance from that fragment to the light, and that distance is larger than the one that is stored in the depth map, right? It's just comparing distances. Literally, just compare distances. Yeah. So someone is asking, are depth map computing using a orthographic or perspective projection, or does it depend on the light type? Very good question. Depends on the light type. Yes. Very, very good question. Yes. If you are using point lights, you need to compute perspective. Basically, this image needs to be perspective. So as you can see, for example, here, this one is perspective. If you use directional lights, this render should be an orthographic projection. Yeah, very good question. Yeah, because basically, again, if it's directional, it means that the shadow should not increase in this direction, right? Which basically is what will happen if you compute this as a orthographic rendering. So yeah, very, very good question. Okay, the thing is, we could have shadow map problems if we are not very careful. So you need to include, the thing is, because it's based on shaders and it's based on creating images and shader passes, you need to include all the shader effects. So this is obviously wrong, right? Because now if I apply, for example, an opacity effect to this object right here. So for example, in your shader assignment, the bonus part, you need to create these objects, basically like a collection of planes that are representing this maple leaves that are falling from the sky, right? And for those objects, you will need to get information from a texture that is basically black and white, and you will determine that portions of those objects or the fragments of those objects are transparent in some areas, right? Like in this case. So if it's transparent, the light should pass right? The thing is, by default, the depth buffer does not include any opacity or alpha effect. And what is the depth buffer? We will talk about this because we still have a lot of like pending topics, right, for our lectures. So basically, the depth buffer for now, think about it as the the already implemented stage or memory chunk in your rendering pipeline that is basically computing depth information whenever you are going or rendering something on our rendering pipeline. And that part from the rendering pipeline is already automatic. The depth buffer is already computing that information all the time. The thing is, it doesn't include opacity by default. So sometimes you need to modify a couple of things in order to achieve this type of effects. And this could also happen, for example, with displacement, right? So if you're assigning displacement things or like very sophisticated shaders to your object, and you want to render the shadow, right? And you just forget that the depth map that you're computing, you're not assigning or considering those effects. You're just going in there and just asking for the depth map automatically to the depth buffer. The depth buffer will tell you something that is maybe not the actual object that you have, right? Because you're adding more stuff. So that is something that it happens a lot. And there are a lot of video games in which, if you look carefully, they have this type of problems. The shadows are not exactly representing the actual object because the object has some effects or shaders or whatever, and it turns out that this not is not correct, right? And finally, the quality of your shadow maps, basically, it obviously depends on the resolution of the depth map. So sometimes just because you have, I don't know, like thousands of objects and a lot of lights or whatever, maybe you want to increase, right, the performance of your system, and you can decide to get these depth maps in a very low resolution, right, which is just make your entire process faster. But if that resolution is very very low or is very bad, right, you can get something like this, right? This is exactly the same process, but using a very very crappy image for the depth map, so you have not enough information to compute, right? And so look, the shadow looks horrible. It even seems that like the object is like flying on top of the floor, right? And you can see all these horrible things. And by the way, like when you see like weird stuff on a rendering, we call them artifacts, right? So you have a lot of artifacts here because just the resolution is not enough. So the trick here is, if this object, for example, is maybe very far from the camera, so imagine that now the column is maybe there and it's super super far. If something is far, you can decrease the quality, for example, of the shadow of something that is very far, because it will not be as obvious, right, from the camera, because it's just basically a couple of pixels on the final image. But if the object, for example, is very close to the camera, you need to have a very high resolution shadow map, depth map, sorry, to compute the shadow. Otherwise, your shadows will look horrible, right? So this is also like the tricks that you can use to get like a very quality image, but not as expensive, right? So sometimes we define the quality of the shadows depending on the distance from each object with respect to the camera, right? So if the object is just very far from the camera, it's just like a very very far car that is at the very end of the scene, that car could have like a very 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 crappy shadow because nobody will notice, right? Good. I think we have maybe 1 more minute for a question, because yeah, we consumed the time already, and yeah, we finished for today. Any questions? Yes. None.
Hey, so I get that shadow, when you computed the distances and the compared the values to the depth values, you're determining whether a pixel is occluded or not. But how does that relate to actually rendering the shadow? Is it just a mere reflection?
No. again, what you will obtain here is either a like a Boolean value, right? Is either I am
Right.
occluded or not, right? 0 or
Right.
1, or you can use shadow map technology, right? This same idea to mimic area shadows, right? So in that case, your shadow occlusion value will not be like only from 0 to 1, maybe it's like, right? Like with floating point, right? And again, the way you use that information on your shader is up to you. What you usually need to do is basically to get that value. Let's assume that is Boolean, is I am occluded or not. You get that value. That could be the multiplier of your diffuse and specular components from your shader.
Well, so are you saying when you render the floor for each fragment of the floor, you have to compute the distance between
Yes.
that and the
Yes.
Okay.
Yes. Yeah, I think what can be confusing, and I mean, maybe what I'm going to say, maybe that was not your question, but I had many times students asking me that what they think is that shadow maps work by basically taking the basically, yeah, like the picture of the object and kind of like projecting like the inverse of this image, projecting that on the floor. But that is not what is happening, right? I don't know why, but a lot of students have thought about that, like, okay, so shadow maps is just getting like a render of the silhouette of the object and then just project that render on top of the floor. No, I mean, right? It's comparing distances from the right. It's comparing the actual distance from this portion of the floor to the light, and compare it with the distance I have stored in this depth map, right? Which is basically representing the distance from the surface that is closer to the light. Yeah. Any other question? I guess not. Okay. Yeah, David. Yes.
Yeah, I'm just wondering, why does this work? Is there sort of like a physics behind it? Because it's kind of makes sense, but like it kind of makes sense to just project the map to the floor, but you said it's not how it works. So I'm not sure what's the physics behind it.
There are no physics. This is just
Okay.
geometry. Don't think it as a physics solution.
Like the physics of the lights diffusing, or like the shadow, or
Yes.
are we trying to make it realistic, or is just something, some trick that just
this is
works?
literally this is a trick. It's fake. It's not physics.
Okay.
You're not dealing. Yeah. This is just fake. This is just as you said the first time. This is just a thinking not as physics but as geometry, right? This is just to know if this
Yeah.
surface is behind this surface, right? So in some sense, it is, geometrically speaking, it's very similar to what we do with ray tracing, right? Because with ray tracing, we get into this portion of the floor, and basically we are shooting a ray to the light, right?
Okay.
To see if there is something that is between me. When I say me, is this portion here, right? Just to say if there's something between me and the light, right? Geometrically speaking, this is very similar, because it's like, okay, my distance to the light is 100 meters. So I go to this to the image and say, okay, the pixel that is corresponding to my position, what is the depth from that pixel, right? If the depth is closer than this 100 meters that I have, it means that there's something that is basically between me and the light, which means that I am occluded, right? So yeah, this is super fake. But it works. It works really nice. It really works.
Yeah, another thing. So when the shadow created by the map compared to the shadow from what's the first one?
The ray tracing?
Ray tracing. Yeah, the ray tracing. Is which one's larger? I think the shadow from the map is blurred, so it's a bit larger than the.
You mean
Ray traced
larger
one.
in size?
Yeah,
No, they're basically the same in size. I mean,
the
if
same.
if it's, give me a second. Yeah, look. This is the ray trace one. I mean, if the position of the light is exactly the same, the shape will be exactly the same. So look at where is
Oh,
the
so the size.
yeah, look at the size. I will leave my mouse here. If I go to the other, yeah, this is the shadow maps. It's basically in the same
Okay.
position, right? The blurry thing that you are seeing here, right? This blur effect, that is some people think that is, oh, that is maybe because it's an area shadow, whatever. No, that is not area shadow. That is just the effect of that we are computing this information based on pixels, right? And obviously, if you imagine that you are projecting, if you are getting information from these fragments, getting information from an image, right? From this image in particular, right? This effect right here is just the low quality, the poor quality that you have on the pixels on this area here, right?
Not
So
sure.
this is just the poor quality. If you increase, for example, the resolution of of this image, and this is now, I don't know, like whatever, like 5,000 by 5,000 pixels. I'm obviously exaggerating. The the border of your shadow will be super crisp, right?
It will be to look exactly like the ray
Yeah,
trace.
if you just increase the resolution of your depth map,
Okay.
you can get
But you say they're
almost,
doing the same.
yes, you can get almost to the quality of ray tracing. I mean, you will never get to ray tracing quality because ray tracing is incredibly accurate in terms of geometry, right?
Yeah, but it's like extremely similar.
Yes, but also
Okay.
again, if you increase the resolution of your depth map that much, you might get like super expensive also, and maybe maybe it's the same computing.
No, the
Right.
important is like the importance is to know like they're the same thing.
Yes,
Yeah.
similar. Yeah, similar thing. Okay,
Thank you.
good. Thank you so much, everybody, and I see you on Monday. Bye.